All right, welcome back everyone to the last talk of the workshop. So before I introduce the speaker, how about we have one round of applause for the organizers for putting this together. All right, so our last speaker will be Alberto Bietti, who's a research scientist at the Flatiron Institute. He's taught quite a lot about training dynamics and understanding kind of how transformers acquire structure. And today he'll tell us about an associative memory view of that. Alberto, take it away.
Great. Thanks so much, Andre. Thanks so much to the organizers for having me speak. It's been a great time here in Berkeley. And thanks for sticking around for the very last talk. I'll try to not go over time because there's a hike right after. OK, so, and yes, there's a lot of Simons and Institute words spread around, but in different orders. So here I'll try to talk about kind of so we've seen a lot of talks in this workshop about transformers and computation. A lot of them were often sort of mostly about constructing architectures or trying to see expressivity results. How can you achieve different types of computations? So here I'll talk a bit more about sort of what is a model of the weights. How can you think of weights in a way that sort of is related to training dynamics? So when you actually train a neural net, maybe the weights take a specific structure, and how could that actually implement certain things? So I'll think a bit more about training dynamics in other talks, but still with the computational aspect in mind. And this is some work that I've started doing when I was visiting Meta a couple years ago with a bunch of people there. And then more recently, I've been working with, so Ishan is here, Jason, and some folks at NYU. And just to give some context, so what is going on inside transformers, and specifically, let's say, discrete data or text, like LLM type transformers. So one key thing seems to be reasoning. And we've talked a lot about reasoning and what might happen inside a transformer. One piece of evidence that people have found, especially in this mechanistic interpretability community, is how you might have a lot of different attention heads that do some sort of logical reasoning inside your network. So this is if you haven't seen this is the indirect object identification task. When Mary and John went to the store, John gave a drink to, and you have to predict Mary. And people have found this sort of circuit of attention heads that accomplishes this. And of course, we've seen many different views on what transformers can express, from Daniel's talk in the very beginning to just the previous talks before. So literally, we've seen a lot of different perspectives from circuit complexity, automata, et cetera. And this usually, most of it at least, wasn't really related to training. And then another aspect that I think is quite important in modern LLMs is just the fact that they kind of tend to store a lot of information. And this is kind of conceptually also the models have gotten bigger and bigger. And they tend to also be able to recall more things. So we would like to kind of understand these two things together and just to see some. So this is a quote that I saw, I think when GPT-4 came out. It's like, rule of thumb, if it's on the internet 5 or more times, GPT-4 remembers it. I don't know if that's true, but it tells you that when you train a model, you don't see the internet that many times in pre-training. So probably you've seen it. You've taken a few gradient steps, and all of a sudden you remembered stuff. And this is if you put into GPT-3, Congress shall make no law, and then it just spits out the First Amendment. So kind of it knows things from the web. And also, these things are very interrelated. So sometimes when you do some reasoning, you might benefit from knowledge of a theorem that you've studied in class or something. So these two aspects definitely are not separate. And so I guess I'll try to give a model, like a way to think of weights specifically, not necessarily transformers in general, but kind of at the micro level what's going on, that is inspired by training dynamics and also hopefully helps us understand both of these aspects, both the knowledge storage and the reasoning aspect. All right, let's keep going. So just a quick slide on the setup. So we've talked a lot about transformers. I won't go too much into detail, but basically we have embeddings at the input layer, token embeddings, positional embeddings. At the output layer, we have these unembedding vectors. These are all in RD. And I will not talk about training them. So we kind of fix the first and last layer, just random. So you will not see sort of word-to-vec things that align to semantics or these like Fourier features. We will not see this in this talk, but we'll think about what happens sort of in the middle of a transformer. Okay, so this is embedding, and then what happens at the rest of the layers, one way to think of it is this residual stream point of view that was mentioned in these Anthropic blog posts, where basically each token here, so T is just the position of my token, ZT is just the vocabulary element at that position, and at first you map it through the sum of these two embeddings, a token and position, and then they just go through layers, and what each layer does is it computes something and it adds it to this residual stream. So you have self-attention, usual formula, MLP, usual formula, and so the idea is like, as you go through layers, you keep adding new vectors and directions to this residual stream. So you could think of this kind of like as a set. So maybe this is like a really sparse vector in high dimension, where if you project it down to some directions, relevant features or like token directions, then you have like a set of a few elements, and you keep adding things through the layers. One way to think of these visual streams, and it'll be useful in the rest of the talk. Okay, and then what do you do with this? You just project it back at the last layer against against all the vocabulary elements, and then you predict the next token. All right, so if there's any questions, please interrupt me, but I'll just start by kind of giving an overview of what we mean by associative memories here. So just a little bit definitions and some first results and properties, and then I'll talk about two different applications to transformers. So one will be in the context of in-context learning, so kind of a basic reasoning task, and the second one is more about factual recall. So you need to remember the capital of France or any other textbook information. That's the second task. All right, so just the first thing, what is an associative memory? And when I think about associative memories here, I think about weights. So you have like maybe a key query matrix in your attention, and I'm going to try to view it as what I'll define here to be an associative memory. So what is an associative memory? You have two pairs of embeddings, two sets of embeddings. So the input embeddings I call UI, the output embeddings VJ. These are going to be assumed nearly orthonormal, so all unit norm and close to orthogonal. And then all you have to do is basically you can define a matrix in this way through all these outer products. So for each pair, you have some kind of relevant associations, pairs of input outputs. Call them IJ here. You stick them into a matrix with some weights. And what does this give you? When you have this property of nearly orthonormal embeddings, basically you can recover these weights by just testing your matrix on the right and on the left by the correct embeddings. So why is this relevant in transformers? Two examples. So one, if you think about key query association, so when you do attention, you're typically trying to map your current token to something in your context. So maybe you have a matrix here that tells you key query. You test the key on one side and the query on the other side. And let's say these are embeddings of words, and you've stored a given pair. Like when my previous token is something, and then like I've seen it in the context somewhere, you want that to match, so you get a high score. Otherwise, it doesn't match, you don't get a high score. This allows you to kind of focus the attention on a relevant pair of, let's say, tokens or features. Okay, so there's one way, and then also when you actually predict the next token, you're essentially somewhere in the network you had some computation. Maybe it's like attention. The output of attention is like taking a key vector and multiplying by this output value matrix, or an MLP. Then here you have this like the output of the MLP, let's say. This could be a memory. And then you try to kind of, if that memory stores an output that is like a next token, that helps you predict kind of a strong probability on that token. Does that make sense? Motivation with transformers? All right, and okay, yes. Good question. Probably not, but we'll see what happens. Yeah. So usually, as I said, these XT and XQ, XK, XQ are basically residual streams. So they actually have a bunch of vectors, not just one. But what you can hope is that if the dimension was infinite or something, they might be nearly orthogonal. But you still have a sum of them. So hopefully you only depend on some of them, or you can filter out the others. That will be a key question. Any other questions? Okay, so just for some background, if you've heard of Hopfield networks, this is very much related. So there's been neural computation has studied a lot about how many things can you store with objects related to this. Usually it's more about you do some dynamics on some energy landscape, but it ends up being related. Usually this literature kind of considers the auto-associative case where like the input and output are the same and you're just trying to check membership. Like, is this did I see this or not? So this is more like a hetero-associative version. And then I've heard from this actually from people at Facebook who are working on kind of retrieval in the context of databases, or kind of like fast retrieval of things. But yeah. And another thing, you might have heard of transformers and associative memories together. That's usually, often that's about a different thing, which is the attention specifically. So it's like retrieving something in your memory, associating, and then if you do many layers, I think Philippe talked about this, and we've seen other, actually Daniel mentioned it in one of the talks. Yeah, so this kind of, you can retrieve things from your context. So here we will not think about this view of associative memory, more about like at the weight level and each individual weights. It won't really matter if it's a transformer or not, but we'll see applications to transformers specifically. Okay, now, first, this maybe this comes from nothing, but just to justify why it's relevant, let's think of a very basic model. Okay, so a linear neural network. Kind of a baby model. So you have an input token, you map it through some input embedding, then you take a D by D matrix and you map it back to all the output tokens. So then you train this for classification, let's say, and you're just training W. The embeddings are fixed. You take one gradient at position W, and it basically takes this form. Okay, it's pretty natural. If you have a matrix, two vectors, the gradient will sort of be this outer product structure. And what matters will be the weights here. And just to give you an example here, if you had a data distribution where you have uniform tokens as inputs, and then your label is just this like F star association of the input, you just want to memorize these input-output mappings. What you can do is even just one step on the population loss, okay? And what that gives you is, it gives you this W1, which satisfies this. So essentially you get perfect classification accuracy after just one step, assuming you have enough data for this to like be relevant. And more generally, so this is like a simple model, but in a big neural net, you might think that there's like an input embedding and then some other computations afterward. And what the VK should be, the output embedding should rather be this like backward vector that you get during backprop. And one thing is like the actual scalings that we take here are related to the feature learning literature. If you've heard of like mu-p and stuff, this is kind of the, we've heard about it a bit this morning, but this is kind of the scaling that matters for feature learning. So you get these kind of like very spiky matrices as opposed to the initialization, which is just a random matrix. And these one-step type arguments have been used a lot in the context of feature learning in neural nets. This is on shallow ReLU networks, and this is actually on transformers by Mahdi and colleagues. And then, so I've talked about how this comes from dynamics, so gradients take this form of associative memories. Another intuition that you can get is in terms of what happens with width when the width is finite. Okay, so let's think about random embeddings with just like D dimensions. This is the scaling that you might take for your variance. What happens here? Let's say we have some associations that we want to memorize from Z to F star of Z. Construct this matrix. The question is like, if you compute these, if you compute this like outer product thing, again, you test it against different embeddings for Z and Y, you get this object. Then you can study sort of its expectation. So for the correct Y, this is 1. For the wrong ones, it's 0. And then you can kind of look at the variance. This kind of high-level intuition, but you can look at this thing and how do you make it small enough so that you can distinguish the correct versus the incorrect. And this tells you how many objects you can store. And so if this were the identity, let's say you're just trying to copy something, then basically this term dominates, and you can store about D squared objects or associations. If this is something where maybe some labels get repeated, you might lose some storage capacity, but you can still store things. Just one comment here, much better than one hot. So if you take one hot embeddings, basically your dimension has to be equal to n already. Whereas here, if you take random embeddings, you can actually have the dimension be the square root of n, so you can gain in terms of how many parameters you have. Yeah.
How does this compare to what happens in the auto-associative? That's pretty like.
Yeah, I think it's pretty similar for like one step, I guess. If you do one step of these Glaber dynamics, I think it's quite related. Everything else is probably similar. But they have like usually binary vectors. Yeah.
Is it also that sometimes you can get away with just square root?
So I mean, the Hopfield literature usually is just vectors, not matrices. But if you do a matrix version, you do get D squared. And then actually, if you do polynomials, which is part of what so Ishan here has been looking at, if you do polynomial versions of, you can store kind of powers of K. That's maybe also related to what we did yesterday on the SSNs. Yeah, so just little extensions that are a bit more transformer related. So in practice, you might have like products, low-rank products of matrices. Okay, so key query, output value. So M here would be the head dimension. D is the dimension of the embeddings. What this tells you is that basically you can get as many associations as number of parameters. And if you think of like I think a 7 billion model is like M is 32, D is like 4,000, 5,000. So that's actually a lot of things in just like one head, and you have lots of heads. So you can store a lot of things in these models. But there's constants that also matter. And here the constructions, just to keep some links to reality and training dynamics, the constructions are like you basically take one gradient step in one of the matrices, and the other one is just fixed at random. So it's something that hopefully is still tractable and close enough to gradient descent, but we haven't necessarily always studied the links with dynamics. So you can go, if M is larger than D, you want something more than D squared, you can add a nonlinearity, and you can actually go higher up. So some constructions here we use with Hermite polynomials, you can like get storage that becomes polynomial in the dimension by just making the width large enough and taking nonlinearities. And another thing is sometimes you might care about multiple inputs. So maybe you're instead of predicting from one token to the next, you want like a trigram. You want to predict from two things what's the other thing. Or maybe it's like factual recall. So you have the word Paris, the word country, and then the output should be France or something. So sometimes you might want these two things. And remember the residual streams are sums. So a nice structure here is like sum of two embeddings. If you put this in an MLP, you actually also get these types of capacitive results. And then you can, okay, so number of parameters equals number of things you can store, actually also ties back to information theoretic things. If you have like a certain number of bits, you can achieve some target loss. And also it still links to like these modern Hopfield nets which actually studied higher powers of D in terms of storage. Yes?
This is so cool. For the number of parameters, is that having to do with the depth of the network as opposed to the width, or?
This is just like a single layer, so a single block. So you can think of this as like one head. Yeah.
Okay.
And this is one MLP layer in the transformer.
So like for the infinite width limit, would this apply to your
Yeah. The infinite width would be D goes to infinity.
Okay,
yeah.
okay.
Okay, any other questions? Okay, so we've seen some basic properties. Now we'll kind of talk about two examples of how you can use this inside transformers. So the first one is about this induction head mechanism. So for in-context learning, you might have seen this before. If you haven't, the point is like sometimes you see something in your context and you want to reuse it later. So let's say there's a sentence that somehow talks about Mr. White. Okay, and if you put this into GPT 3.5, when Mr. White went to the mall, it started raining, then Mr., it predicts white. Okay, it's not going to make up another name. It actually likes to use the same names in its context. So it makes sense in language to often reuse kind of rare words. It makes sense to reuse the ones that were in context as opposed to just making something up. And so then we have a toy model, but maybe a lot of the rest is a bit more knowledge-based, but some of the things that matter here might be from the context. Some other things might be more from the training distribution. So we want to also try to model these two things slightly separately. So the model that we define here, kind of a toy model in which we run experiment and do a little bit of theory, is we define these trigger tokens. Think about this Mr. or Doctor or something like that, which has a proper noun right after it. And then every time we sample a sequence, we generate some corresponding word. So in this sentence, it will be white. So anytime I see Mr., it'll be followed by white. In the next sentence, maybe it's Obama or something else. And then it'll always be Obama after Mr. And then how do I generate the sentence? It'll be just a Markov chain. So everything comes from like a general distribution here of bigrams. Maybe it's like the one that Shannon trained in the 50s, I think. Anyway, you can train some bigram model, but then every time you end up on the word Mr., then we use this special bigram and we predict white. Okay, so in practice, what we do is we take this character level Shakespeare, estimate bigrams, that's our pi b, and then we just generate random tokens for this in context prediction. All right, so how do transformers do on this? One layer fails, two layers work, and if you've seen the previous talks, this is kind of natural. It's called an induction head, and in fact, one layer is not enough for induction heads, as Clayton, Matoush, and Daniel showed. 55 seems high, but there's some like shortcut solutions that do well, that's why. And so what is the induction head? Okay, so the first layer, so basically you need 2 attention layers to do this in context retrieval. But yeah, also called associative recall, as people yesterday. So depending on the days of the workshop, you might have heard different names for this. But so T to T-1, this is a positional kind of key query attention, and then the output value matrix looks at the actual MR, and it copies it here. And then the second layer just looks at MR, attends based on MR, and then copies white. Okay, so you attend on the trigger. At first, you copy the trigger, and then you attend based on the trigger. And you can see this on the transformer if you train on the synthetic task. Just to go back to like these associative memories and how you might do this with associative memories. So remember, I'm going to use random embedding, so I don't train them. You can also train them, and it still works, but let's just stick to random. So these are kind of, if you have dimension D, you can hope to expect something 1/√D type. Another important thing is if you actually leave a matrix at random initialization, maybe the value matrix, it's actually a helpful primitive because it kind of rotates your embeddings in a random direction. Okay, so when you copy this trigger here, MR, from here to here, it's actually all of a sudden in a different space. Why is that useful? Well, if you then have to match MR to MR, you don't want to match to this MR, but this one, right? Position T+1 and not T. So it's helpful to have colored it differently or somehow rotated it in embedding space. And so we have these primitives. Now we can actually define 3 matrices. And these are our associative memories, so they're just outer products. Okay, the first layer is just outer product of positions. This is you just try to attend to the previous position. The second layer attends based on this trigger, and the second one of them is like with this tilde, which is like this remapping by the first layer value matrix. And then at the end, you want to kind of take this the B token and somehow map it to the output space. So you take EK and you map it into the unembedding. Does this constructor make sense? So you only need these 3 matrices to implement the induction head. Okay, so another thing is attention kind of has to focus on the correct token. So you might want to like rescale. If you rescale this matrix, sort of it makes the gap between the correct token and the other ones larger, and then the softmax hopefully focuses. So that's another thing that you need to do. And if you're not fully sparse, you're going to have some noise, but hopefully that noise is not too large. Does this match practice? So the nice thing is like here we actually have a model of what the weights should be. So we can actually test this model empirically, check the weights, whether they satisfy these types of behaviors. So in practice, what we have is these memory recall probes, we recall them. And then here, so when you have a matrix here and you want to check if it has this behavior, you just test it against all the VJs, take the argmax, and does it match? And what you see empirically is if you train all of these 3 matrices, basically all these recall probes go close to 1. So they're actually having the similar matching effect. So the associations tend to be the correct ones. And another thing you can see is there's a bit of an order in how these things are learned. It seems like if you don't train the value matrix of the second layer, things are stuck. So it's important to learn that first. And once you learn that, that can be learned kind of by itself, but then you'll start learning the other 2 key query matrices a bit more slowly. If you train everything jointly, it'll be faster, but it's probably harder. So for the analysis, we kind of think about this 1 step at a time sort of analysis. And we also simplify a lot of things. So this is to say we do a little bit of theory on a kind of an ideal setting for what can you do in this task. So particularly, we only have data where you have to predict the second induction copying task. Everything is uniform. Some things are cut off in the architecture to make things simpler. Infinite width, infinite data. And yeah, we need like not too long of a sequence length. And then you can kind of take one step, and things sort of match the predictions of or like these constructions. So one key thing is like when you look at one matrix, let's say the value matrix, usually its input in the beginning is just the sum of a bunch of embeddings. Everything, because the attention at initialization is uniform, so you have a bunch of things. And the point is that you have to capture the correlation between some token in the context and the label. So it turns out that if you see the word white as the label, there actually will be a white in your context for the second prediction. So then you can make the link, and then everything else is noise. So you end up capturing this correlation. And then you can do the same process at the middle layer, which remember, like it takes the middle layer. Yeah, well, like the key query matrices will tend to like align to the correct token, but still their inputs are still noisy because the very first layer is still a bunch of noise. So you have to capture all these correlations, and it's a bit complicated, but you can do it. And yeah, I should mention that. So if you do just one layer of attention, this kind of showed up in these two papers previously, one of them by Mahdi here and colleagues. And in particular here, they have finite sample results, which is a very nice and open question for people here. OK, so just a little bit more insight. Yeah, I talked about how when you have a bunch of noise in your input, so let's say your input embedding here is not just like one token, but it's a vector x, then the gradients, instead of just depending on like specific output embeddings, they depend on these conditional expectations. And this can help you kind of filter out all the noise and just capture what's relevant. So you can have another example here, but I'll skip it in the interest of time. One last point I want to make on this is global versus in context. So I talked about how you had both the in context predictions and also these global bigrams, so syntax versus the nouns. So if you actually train on everything and you add an MLP layer, what seems to happen is that the loss, so this like dashed loss here is on the global bigrams, so predicting what's just this Markov chain, and that goes down very quickly. Whereas, okay, it's hard to see, but some of these, at least the purple line, is much slower. This is the in context predictions. So the loss on the in context tends to be much slower, and that's potentially because you don't see as much of it, or you have to like figure out this attention mechanism, which takes more time and samples. And you also see that the feed-forward layer, this is a probe for the feed-forward layer, kind of a KL divergence, that goes down very quickly. So very quickly, the feed-forward layer in this toy network seems to fit the global bigrams more quickly. And now you can do a little bit of experiments too. So this is this is the Pythia models, which we've heard about this week. So what you can do on Pythia is like you can actually train on this problem where there's a bit of a tension between, do you use the context or do you just use sort of syntax? So if you type in ChatGPT, Madrid is located in, or this was Pythia 1 billion, it tends to tell you the instead of Spain. And maybe it tells you in the north of Spain, actually. That's the actual prediction. But let's say you want to predict Spain instead of the, then there's kind of a tension here. And so one thing you can do is kind of ablate away the late MLPs. This is something that people have done, particularly this laser technique. And what you see is, this is through training. So Pythia, you have everything through training. One thing you see is that these global, so I just call it like a global bigram. It just depends on in. Like after in, you're likely to have the. So this gets learned very quickly. More like a syntax thing. And much later on, you get this in context. And what you see at the end is that the gets predicted highly, but if you get rid of the MLPs, all of a sudden it's switched. So Spain gets predicted more accurately. So you're promoting the in-context association. And so we have a little bit of theory in a toy setting that tells you that actually it's normal that MLPs pick up things much more quickly than attention, mostly because there's a lot of noise in these attention embeddings, so that takes more samples. Okay, any questions on this part? Yes? Yeah, it's weird, yeah, because it's actually a factual thing, but at least it doesn't depend on the last token. So the point of the MLP is really the residual connection. That makes it really easy to use the current residual stream as opposed to anything else. Whereas if you want to figure out something before, like the fact that you're talking about Madrid, you have to attend to context, so you can say that that's in context. But I agree that this specific thing is more like factual recall, so you might think that MLPs also play a role, and in fact, they do for just associating Madrid to Spain. Okay, so given that we're talking about factual recall, let's talk about these more recent results. This is not an archive yet, but hopefully it will be soon. So here we have a different task, which is more about how many things can we store. And the usual use case for this is factual recall. So the capital of France is Paris. You're given the subject and the relation. You want to try to predict what the attribute is. So you have a set of subject tokens, a set of relation tokens, and then corresponding attributes, this A star of R. Here we assume actually that all the attributes, like for any specific relation, the attributes are different. So there's no overlap between them. And then what else do you have? Like a bunch of language. So instead of modeling language, we say it's easier to just call it noise. But hopefully linguists will help us fix that part of the model. But okay, the question that we asked then is like, how hard is it for a transformer to learn this? How does a transformer solve this, and also how many parameters do we need? So we would like to understand both dynamics and sort of capacity, how many parameters we need. So for capacity, we have some constructions based on associative memories that I talked about in the beginning. So this you can do this with one layer or one layer plus an MLP. So we have kind of slightly different constructions depending on whether or not you put an MLP afterwards. We use random embeddings. These are so we have embedding dimension, head dimension. We can also play with the number of heads here, whereas the previous section was just one head per layer. But basically, if you use an MLP, then you have these constraints. So you need the total. So the MLP basically needs the total parameters of the MLP needs to be S times R, which is basically the total number of facts that you want to store. But then we have some lower bound on total heads times DH, but that's not too bad. That's kind of required. And overall, this still ensures that the total number of parameters is S times R. So S times R is basically the total number of facts. In the attention-only case, we kind of need this lower bound on D, which could be a little bit worse. So you might end up, depending on this number of possible facts for a given relation, which could be large, but yes. No, it's arbitrary. But the A, you mean the A star thing? Yeah, so all we assume is that the outputs are in different sets, actually. So they are disjoint. But you could think of these of all being of the same cardinality, and you're picking at random or something. Okay, so we have constructions that are based on associative memory, so there's some hope that they're related to training dynamics, but we don't have that for this construction yet. The other thing is you can make the sequence larger and put a lot of noise. That only affects log factors. It doesn't really matter because attention can kind of extract away the subject and the relation in these models. And you can plot what happens empirically, at least. So you train a lot of these models with different number of parameters, different widths versus hidden widths of the MLP. And overall, so one thing you see is that you can also, if you use both attention and MLP, you can play with how many parameters you put in the attention versus MLP. You see this kind of, we said you have this lower bound on the head dimension here. So there's some cases where if you only use attention, you have a bit of a limit, but otherwise, this is very idealistic, but we have like a kind of a line. And then here you see different scalings of how much the width versus the hidden dimension, how they vary with each other. And you see that typically the number of facts stored, meaning how many how many parameters do you need to succeed at this task, kind of scales linearly with the number of facts. Number of facts and number of parameters scale linearly. Okay, so this was the constructions. We haven't really talked about dynamics. So for dynamics, we don't really, it's still kind of ongoing to see what happens when you actually have these non-orthogonal embeddings. So you just use one-hot embeddings, and here you can study sort of gradient flow with a small initialization. You have no critical point, no spurious critical. With this initialization, you always converge to zero loss, so you kind of succeed at the task at the end of training. And another interesting thing is you can kind of predict in the theory that there's an intermediate stage where basically you're only using the relation to predict things. Okay, so we call this hallucination because basically it's like you figured out that I'm asking for a city. Let's say that Paris is the capital of, you figured out that it has to be a country, but you just like output a random country. You don't know which country it should be. So yeah, basically the model can pick up the relation token a little bit more quickly, but it doesn't really know how to differentiate different cities. Yes. Yeah, basically. So there's kind of like this stepwise learning behavior. So you can see it here. If you plot the loss, there's this intermediate stage where basically if you compute the cross entropy loss when you predict using this bad predictor, it sort of matches what's going on. Okay. Concluding remarks. So we've talked about various things, but mainly the message was this. Oh yeah, sorry. Question.
Is there any reason for why it uses just the relation as opposed to just the subject?
Yeah. So okay, it's kind of the data set plays a big role here. So it turns out that we have, so for each relation, you can have like many different facts stored, whereas for each subject, maybe the number of relations is minor. It's not that large. Yeah. So kind of it's just relative step sizes in the population loss.
This is a clarification. So
in the example you're talking about, it's really like a function, like capital of versus a general relation. So is
Capital of, yes.
like the capital of relation happens to be a function. But is there a difference? Like did you also consider settings where it's like a relation where like the output is non-deterministic? Because it seems like for predictive tasks, like storing functions is maybe more useful if you're trying to predict the second argument.
So what's an example? So
Like-
you're saying it's a function. So by function, are you talking about this A of SR here?
Yeah, like
One to one.
Oh,
right, like capital
Oh,
O
I see, I see.
maps France to Paris deterministic.
Oh, I see, I see. Yeah, yeah. So we are using, deterministic model. So that's,
Okay.
whereas it could be multiple cities or something, I think. Yeah.
Yeah, exactly.
Well, usually capital
city
is.
of France. Like there's
Oh, yeah, city of, there's many possible choices.
Yeah.
In which case, there could be like a hallucinating thing that is actually the right thing. Yeah.
Yeah.
Yeah. So you could try to think. So a lot of these models tend to be deterministic in the modeling assumptions you make. If you add noise, I think that's an interesting next direction. Try to see what happens if they have right. Great question. Any other? Yeah.
In dot landscape where the linear attention is kind of a factorized model.
Yeah. But plus a logistic.
Saddle or something.
So it's a saddle at infinity. So it's like if you actually went all the way and pushed your weights, it would be a saddle. But in between, you don't actually get the saddle. So yeah, if you put like very, 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 very small initialization, you might reach that infinity thing. But just vary, you stop here and then you actually keep going down because there's no spurious minima or finite. Any more questions? So I'll just conclude with the last slide, and then we can go on a hike. This is the last slide. Okay, so we've seen benefits potentially of viewing weights as associative memories. You can get kind of tight capacity bounds and also some links to optimization, particularly with one gradient step, but also potentially more gradient steps. And then we've seen how this is helpful inside transformers to model, for instance, these induction head behaviors, MLP versus in-context learning, and then the factual recall task. We have some extension on the kind of more toy setting where you just do classification, so just this linear network case. And here you can study what happens when you have finite data and finite dimension and sort of a power law scaling. And you can think about what optimization does to your predictions. We also have something about what happens if you optimize these models using gradient descent. Often it's very messy, especially if your embeddings are somewhat correlated. You get a lot of spikes and oscillations. And there's a lot of future questions that I think are interesting, so please talk to me. So finite sample would be great. Thinking about more complicated reasoning tasks beyond this just two-step in context recall. Better understanding of optimization, and particularly if you do jointly different layers, et cetera. And then what if you actually learn the embeddings? Those are all interesting questions. And thank you for your attention.
Questions for Alberto? Good. Okay. Let's
Let's go in a row.